Good morning to all. In today's session, we are going to discuss about the superplasticity, especially in composite materials. What is superplasticity and what are their characteristics and benefits and applications also we are going to discuss here. In superplasticity in composite materials, first we should know what is the definition of superplasticity. Superplasticity is the ability of a material to undergo significant plastic deformation without breaking or fading. In composite materials, superplasticity is achieved by combining two or more materials with different properties to create a new material with enhanced deformability. And next, characteristics of superplastic materials. What are the characteristics of superplastic materials? The first one is the that means the strain rate is high. It means high strain rate sensitivity. It's nothing but the ability to deform at a high strain rate without a failing. And low flow stress also. Here it can deform at relatively low stresses and elongation with a high level. Can undergo significant plastic deformation without breaking. Then we can go for the next one is benefits of the superplastic composites. Here the formability is improved. It means the formability can be improved into complex shapes without cracking or breaking. And enhanced toughness is another benefit. Can absorb more energy without failing. Finally, reduced weight is another benefit of the superplastic composite. We can replace heavier materials while maintaining the performance due to the reduced weight. And we should know the applications of the superplastic composites. One is aerospace and automotives and medical. These are the main areas of superplastic composites used. In aerospace, it is used because lightweight, high performance components for aircraft and spacecraft components. For automotive applications, complex shaped components for vehicles such as dashboards and bumpers. They are the applications for automotive sites. In medical, implants and devices that require high deformability and biocompatibility. For that, a medical application is very much essential for superplastic composites. Finally, what are the examples of superplastic composites? Titanium alloy composites, carbon fiber reinforced polymers CFRP, metal matrix composites. These are the examples of superplastic composites. In titanium alloy composites, it combines titanium alloys with ceramic or metallic reinforcements. And carbon fiber reinforced polymers, here it combines carbon fibers with superplastic polymer matrices. Finally, MMC, it is called metal matrix composites. It combines metallic matrices with superplastic reinforcements. Then we should aware of the challenges and the future directions. One is scalability, interfacial bonding, cost reduction. These are the challenges. Scalability, it means scaling up production while maintaining superplastic properties. And interfacial bonding, here improving the bonding between the reinforcements and the matrices. And cost reduction, here we are going to reduce the production cost to make superplastic composites more competitive. And mechanisms of superplasticity we are going to discuss now. The mechanisms of superplasticity involve the ability of a material to undergo a significant plastic deformation without breaking or failing. And the main mechanisms include here, one is grain boundary sliding. Sliding of grains along their boundaries, allowing for deformation without a significant grain rotation or fragmentation. Dislocation motion. Movement of dislocations within grains are enabling plastic deformation without grain boundary sliding. Third one is diffusion creep. Deformation through diffusion of atoms or vacancies, allowing for grain boundary sliding and dislocation motion. The fourth one is grain rotation. The rotation of grains during deformation, accommodating shape with changes without a fragmentation. The fifth one is interface controlled deformation. Deformation controlled by the sliding and migration of interfaces between grain surfaces.